Hello, this is my DIY thrust test stand. I made a intro video about this a few months ago, actually it's about 6 months ago now I think, and I said I was going to make another video later and release the source code and explain in a little bit more detail about how to put it together if anybody else wants to give it a try. So that's what this video is going to be. Yeah, sorry it's taken so long. In fact, pretty much everything we see here, I actually had that ready back in April. And all I've been doing since then is just working on the software side of it every now and then, adding some new features and trying to maybe fix some bugs, and also writing some documentation and tidying everything up and putting it into GitHub. So this is the GitHub page here. I'll put a link to this in the video description and you can take a look at that. And I've done what I consider to be a pretty good job of explaining everything in this document in the main README here. So I'm just going to use this as my script, so to speak, for this video, and I'm just going to go through this for the most part and just look at what it says and show you a quick example of doing calibration for the sensors, and I also want to show you what I've set up for you can submit your test results to the server and you can see other people's test results, although I'm not sure how far I'll take that. I might just stop working on that because there is, as you may know, there is this site called MiniQuad Test Bench, and the guy who's running this, Ryan, this is really well done. So I'm thinking what I have is just really not worth pursuing when there's this much good data out here. It is kind of nice to sort of crowdsource something like this where you can get lots of people to do a little bit of work each and bring all those results together, but the trouble is you've got to build one of these kind of contraptions, so there's quite a bit of outlay or effort to get started, and comparing what one person tested on their machine with what somebody else tested on another machine, you're not really getting a direct comparison by testing it on some slightly different machine, I think. So as far as comparisons go, it's much better to have one person with one test stand doing everything, doing all the work. So I don't think I'm going to go through any further with my online sort of side of this test stand, but I'll see what people say about what it looks like so far. It's very rough what I have at the moment, but it's functional, and he's got really nice setups here for you can interact with these graphs, choose a different motor and so on like that. So this is really awesome. Lots of detail too, so well done, Ryan Harrell. I really like this site, it's great. So anyway, back to this. So yeah, you'll need a 16 megahertz Arduino, and I have made binaries for Linux 64-bit and Windows. I think the Windows one is 64-bit as well. I'm not going to make a Mac build, so don't ask for that. And the sensors that I have set up are a load cell, obviously, to measure the thrust. There is a current sensor and a voltage sensor. I'm using a Hall sensor for the current, and I'm using an analog to digital converter to measure the voltage, and that's using a voltage divider to bring it down from the battery voltage, which is, well, whatever it is, down to something that's within 0 to 5 volts for the ADC to work with. And I also have this little laser unit here which is shining through the propeller area onto the receiver at the bottom, and the propeller will swing through here and break the connection between that laser to measure the prop speed. So those are the sensors that I've set up, and I've explained them all here. Yeah, one problem I came across, I originally thought was going to be making this video about 6 weeks ago, and I tidied up all my source code and everything, and then I thought, okay, that's good, everything's working on Linux, I'll just quickly switch over to Windows and port it to Windows because it's Qt project, so it's quite easy to port. But no, God, I had endless problems. So to make a long story short, if you are running this on Windows, do not use an Arduino which has one of these CH340 or CH341 USB to serial chips. It's not going to work. You may be able to use Arduino programs, like upload sketches onto it and so on, but for whatever reason the libserial port library that my program is using, it just does not play nicely with this CH340 USB to serial converter or adapter or whatever they're called. But it does work just fine with oops, what happened there? It does work just fine with the official Arduinos, or the Arduino Uno at least, that have the ATmega 16U2. Is it? This is what's talking to the USB on the computer, isn't it, on this one, I think? And it should also work with a proper FTDI adapter as well, instead of one of those. So if you're having trouble on Windows, yeah, that could be the problem. And the trouble that you'll see is that the graph updating is all stuttery and slow, and you can't control it very well, and it's just horrible to use. Just the communication between the Arduino and the computer is not very good. On Linux though, both of these work perfectly well. So I'm going to continue using this one on my particular test stand, because this is the one that has these nice double rows of pins there that you can connect a male and female of each pin. It's very, very handy because you do need a lot of connections, and there's some other stuff broken out there which is quite nice. So the connections, I think I'll just skip through this pretty quick because I've actually described some of it already, but on the left is the component in question, and on the right is the Arduino. So I've listed up the connections like that for the ESC. Again, you have left is that component and right is the Arduino. And I've just written a little bit about each one of these components as well. This is the load cell amp, and I've had to do a little bit of fiddling with this, because when you buy these, they are set up to be 10 Hertz update rate. So it's 10 updates a second. It's not really that fast when you're trying to measure something like this, but they are also capable of 80 Hertz update rate. But you need to mess around with these two pins here. You have to detach this pin from the pad on the PCB, and you have to connect it to the one next to it. So what you're trying to do is you're trying to bring this pin to logic high by connecting it to VCC, which is there. And it's quite small and tricky, and you have to be rather careful to do it, but it's not impossible. So analog to digital converter, you'll need to make a voltage divider of some kind. Probably about 10 to 1 is fine. This one has quite a few connections because I've used this as this analog to digital converter has two, well, it has four actually. If you want to use all common grounds, you can actually have 4 ADCs running on this one module, but the way I've set it up is I've given them each their own ground. Probably not really necessary, but then that gives you 2 ADCs, and I've used those for one for voltage and one for current. So that's how it's set up there. You don't really need to look at that because it's sort of described here what you need to do. Just thought I'd put this photo in here just in case it helps. And this is the hall sensor, which is down there with these connections. And you'll need to, I found it easier to take this little plastic thing with the screws on it, take that right off and solder directly onto the pads like that. So you need to break one of the power lines, either the negative or positive, I don't think it really matters, and you'll need to bridge that through this sensor to measure the current going through there. The one I have is up to 30 amps, which I think should be right for most of the stuff that I have to test, but you might want to get a higher current rating than this if you're going to test big motors. And then this laser TX thingy, that's pretty simple stuff. I highly recommend putting a buzzer on, because you can use that for feedbacks and warnings to let you know that it's about to start up. Speaking of which, there is potential for injury. There's no concept of arming or anything, so just be careful, don't cut yourself. So I've listed up some basic usage here and some stuff. So this is what I'm going to go over now, and we'll have a quick look at this stuff. And right at the bottom here you can see where I've linked to the binaries for Linux and Windows. And there's a little bit about building there. I'm not really expecting anybody to try building it, but this is the Qt versions that I've used to build it, and should build okay. I don't know. Let me know if it doesn't. Maybe we can figure out what the problem is. Alright, so enough of looking at text. So I have this set up here, and if I just start the program and click open to connect, I see my values coming in, and if I just push the motor there a little bit, so I was just oops, put it all on one screen. Now I'm not taking my own advice here because the battery is connected, but what I'm doing is I'm just going to push it with something else. But you can see there that the thrust is being measured. So that's probably the most basic measurement you want to take, isn't it? The thrust. And I can do this to control the motor speed manually. So I guess probably the first thing you'd do is to calibrate the sensors. So let's have a look at how you would do that. How small can I make this? Oh yeah. Let's try putting this here. Okay, so calibrating sensors. We have voltage, current, and the thrust. So I'll do them in the opposite order, I think. Yeah. So I'm going to disconnect the battery, and I'll calibrate the thrust first, because this is the easiest one to demonstrate. So you need to measure the zero situation and also the situation where you're measuring a known quantity. So the known quantity I'm going to use is 100 gram weight, which is like that. And I think I'm repeating some of this from my first video, but bear in mind that some people might not have seen the first video, so it wouldn't hurt to repeat this a little bit. So with just the prop on the motor, I'll click measure 0, and if your thrust was not already showing 0 here, it should after you click this. Well, okay, it's not perfect, but it'll be close to 0. And then I'll put my 100 gram weight on and then click measure known weight. So I just have a little piece of fishing line here so that it's not too heavy. Get on. So when you're doing something like this, you kind of want to have the battery disconnected, alright? Anyway, well, you can see I've calibrated this just before, so it's already showing me that measures at 100 grams, but it won't be the first time you do this. So at this point you just click measure known weight. Nothing's going to change for me, but that now lets it know that what is measured, what it's feeling at the moment is 100 grams. Alright, so remember to take that off. Very important. Okay, so to measure voltage, I will well, firstly, with it battery still disconnected, so I haven't plugged it in there, you'll click measure 0 here, and again it's not really going to change much, but you should see a 0, pretty constant 0 reading for voltage now. And then you plug your battery in and you measure the voltage of the battery. So when I plug the battery in, we'll see this orange line has come up to a higher value now, so it's sensing the voltage, and as before I just calibrated this earlier, so it should be about 11.42, but just to double check, let's see what we get. So I'm just going to measure it from the balance port of the battery, which is over there. So it's 11.42. Is that what it said before? Okay, so I'm just going to leave that there, but what you would do is 11.42 is what we measured as our known quantity, and then I'll click measure voltage there. So it's not going to change, but that's how you do it. Now current is the same. So at this point we have 0 current, so I'm just going to click measure 0. So it's reading slightly non-zero value at the moment. Measure 0. It might actually be better to do this with the battery disconnected. I'm not sure. Won't make a whole lot of difference, so I'm just going to do it with the battery connected. And then now this is a bit of a tricky part, because we need to have a non-zero current going through the hall sensor, and to do that we need to have the motor spinning, and we also need to have a break in the power line. So the way I've been doing this is I got one of these XT60 pairs and I just connected them together, but only one wire is connected, so the red one is just separated there instead of soldered on, and I put this in between there so that I can connect my multimeter across here to measure the current. So let me just set that up. It'll take me a moment to get it done. Okay, so I have my current meter reading the current now, and if I spin the motor a bit, we'll see we are getting current reading. So now I can enter a known value of current and click measure current to measure it. But I need to set a current first. So what you need to do is set it to about a medium value like that, and enter that in. Oops. It's a bit hard to get it exact because the value tends to go down slightly as it's running. So there's actually 0.433 when I clicked measure current. So it's not going to be exact, but let's see how close we got it by comparing what it says on there and what it says on there. That's close enough. So you could probably do a little bit better than that, but I think I'll leave it as is. So that's how you do calibration. Right, I guess the next thing to look at was defining a test. Yeah, let's look at that. So you define a test by entering rows of text into this little dialog here, and if it doesn't recognize the value that you've entered, like if it's just garbage, you'll see nothing underneath this past result section. If I just put that back how it was, you'll see that it's recognized those two lines as a beep of 1 second, and then we're going to set a constant RPM of 3000 RPMs for 5 seconds. So this is what the automated test is going to do. Let's just take that one out and I'll show you what this does when I do start test. I'll get to the parts in a minute. So all that does is beep for 1 second, and you can see in the text output here a little bit of info about what it recorded for that task, but there's actually nothing to record for that one. So let's do a S is for speed, and we'll do it for 3 seconds, and we'll make it 1300 microseconds pulse. So if you want to know where I'm getting this from, or if you want a reference for it, it's on near the bottom of the GitHub page. We've got some examples of how this is formatted and what other types of things you can do. Oops, so let me just, so this time we're going to run at 1300 microseconds for 3 seconds. And we should be able to see the prop spinning there when we do this. Pretty straightforward, I think. So yeah, you can just list as many as you like of these. So I could do, let's make it a little bit shorter. Make it 11, 12, 13. Start test, go. Alright, so you can see some text coming in to this little text box here, and wait, by the way, you can stop something, and if you want to look at the graph before it goes away, you can stop and start it with this button. Yeah, and you can turn on which values you want to show on the graph there. And raw values is just the unsmoothed values that were the actual readings that were taken from the sensors. And some of them have quite a bit of smoothing, especially the RPM, because that's a very rough reading. But don't worry about that for now. So you can see here that last test that we had was a 1300 microsecond length pulse for 2 seconds. So it's showing what parts that was for and how many samples that were taken that were good samples. And a good sample is something that is within, I think, 5%. I'm not sure what I set it to, but I think it's within 5% of the target. The target in this case is a microseconds value, so we're never really going to be off that target because that's a direct value that we set. But if we were trying to do a constant thrust test or a constant RPM test, we can't actually set the RPM or the thrust directly. We have to sort of use a PID controller to adjust it, which means that not all of our samples are actually going to be within the thrust range that we tried to get to. So that's why this samples is counting how many were good samples. And this is just the values average for that 60 sample set. So it was, obviously this is going to be the average because that's what we set directly. Thrust was 66 grams, voltage is 11.2, etc. So this gives you an idea of what you can set your other test types to. The other tests being constant throttle, constant thrust and constant RPM. So let me just run this at full throttle for a bit so that we can see what values we're getting for RPM and thrust. Alright, now stop that, and if you mouse over you can see the values at that point. So if I put my mouse in the middle here, we see that I was getting 324 grams or so of thrust and, what does it say there? About 8,000 RPM. So now when I'm doing I'll change this to a T, so it's going to be constant thrust, and if I leave it like this, it's going to try and do 1100 grams of thrust, which is impossible because we just saw with full throttle we're only getting 320. So be very careful not to do this, because this, I don't know what will happen. I've never actually tried it and I don't really want to find out, but probably the PID controller will go a bit funny and it will just set it at full throttle all the time. If you're kind of expecting that, maybe it's not a problem, but if you're expecting it to be a little bit more tame and all of a sudden you get huge bursts of full throttle, it might freak you out a little bit. So let's see if we can do a RC model reviews style 150 grams constant thrust test. And because we're using a PID controller to adjust the throttle based on the thrust reading that we're getting, we need a little bit of time to take that feedback and adjust it properly. So for these constant throttle and constant RPM tests, you're probably going to have to give it at least 4 seconds, maybe 5 seconds is good. So we can try this and run this test. 150 grams, see? And again, stop, and we can see at the midpoint of that test there, oh, that's good, isn't it? 149 or 150 grams. Quite nice, but notice it doesn't do that for the first couple of seconds. You need a bit of time to settle into it, and then after that it's quite good. And what else have we got? 2 amps, 11 volts, blah blah blah. Okay, and over here you can see from that 5-second period we got 198 good samples. That's not too bad. Average thrust was 149.4 grams, and then you can see, you know, voltage, current, power, efficiency, all that stuff over there. So that is a constant thrust test, and we can see there that that was about 6,000 RPM. So just as an example, to do an RPM test, 5 seconds again, let's make it 5,000 RPM, a little bit slower. And because the RPM reading is kind of rougher, it's probably not going to match it as well as we would like, but let's see what happens. So you might have been able to tell that the sound of the motor was just sort of a little bit up and down. But what did we get there? 4,688, 5,200. But on average for that 5-second test, we got 145 good samples, and the average was 5,016 RPM, which is not too bad. And that's 104 grams of thrust. So that is how you define and run the tests. And we've done calibrating sensors. This update list button just updates the contents of this list. So if you start the program up and then you plug in your Arduino afterwards, you can click on this to get it to just refresh the list. Otherwise it doesn't show up your Arduino in this pull down. Okay, so about selecting parts, you click on this dialog, you'll be shown a list of, or some tabs where you can select the parts that you're using for this test. There's not many in there at the moment, so there's just some that I have manually entered. So you can select a motor and ESC as well, like that. The stuff at the bottom, I was intending to use this as a filter. So for example, for props, if you did HQ or something like that, or actually wait a minute, maybe something like that, it would automatically filter this list above so that we wouldn't see any gem fans. We'd just see this diatone one only, but that is not implemented, so none of this stuff at the bottom of these dialogues works. It's only this combo box at the top that actually functions. So when you first get the program, you will find these to be empty, but to fill them you go to the last tab on the right, and oh, it still says dialog here. That's not very good, is it? I have to change that. And then you can click on this button to pull the info from the server, and then it will update those combo boxes to show you the contents. So how you get data into those combo boxes and why you would want to bother selecting it is the next question. So let's have a look at this. So I've got a couple of pages here. There's the reports and the parts. So this is the part that I was saying I probably won't work on much in the future, but I'll show it to you anyway, since it's here and maybe somebody will be interested to look at it. So we have categories of parts here, and you can click on here and you can add a new one. And I just realized that the prop that I'm using here I haven't actually added, so I'll add that while I'm doing this. And you can add a maker. What is a maker here that what's something I haven't put in here? I just thought of this one now. I don't think this is really a thrust test stand kind of a brand, but I'll just add it anyway. So you can add that into the list there, and that one will show up when we do a pull to get the data. So we have MCU types, and these are made from a maker and a name. Firmware type is basically, that's all there is at the moment, I think. This is for the ESCs, and this is just a firmware type and a version. Material is mainly for props. Motors are a maker, a name, a diameter, height, and a kV. ESCs are maker, name, and then the type of MCU they're using. Oh, I thought I had a busy bee in there. No, I don't. And the current rating. So you can add all stuff here. If it detects that there's a duplicate, it won't let you add that one. And propeller is maker, diameter in inch, pitch in inches, number of blades, and material. So pretty sure that one I have there, I have not added it yet, but it's a gem fan, 50, 45, 2 blades, plastic. Yeah, so okay, yeah, I didn't have that one. What? Oh, there is a. Of course, it's the last one on the list. Yeah. Okay, so now I've added that, and I added Immersion RC as a maker. So let's go back to here, and oh, we don't get to directly see makers in this list, so we won't see Immersion RC coming up in here. But we should see that 5045 2-blade that I just added should show up in here, and it's not there at the moment. Yeah, okay, so it's this one here. Yep. Alright, so that is how you set your parts for the test. So that's going to show up in here, those 3 lines. And then these results that I've been running, if you click export results, you'll be able to see the results of my last test, which was what was that? Constant RPM, I think that was. But if you run, well, I only had one in that test, but if you put multiple tests in the same run, you'll see them all here. And you can save that to a file just on disk, and you can do pretty much nothing with that file at the moment. I just thought it might be a useful thing to be able to save to look at later. So you can't load it in to a program and do anything with it. It's just some JSON text. But this upload button here, if I click on here, we should see, if I just go back to my web browser and So this is the set of results that I have been adding, just some test results here. And now that I've added my prop, I think I'll just run that test again. Let's do it this way. Let's do a constant thrust or constant speed test for 3 seconds at 1500, so it's going to be mid throttle, and then we'll do constant thrust of 150 grams for 5 seconds. So I'm going to have 2 results in my test. So I'll run that. You can see it running. Oh, you can see the current too, because that's all connected still. Let's go like this. Start test, and this dialog just reminds you if you've been doing multiple things that's what the test is going to be recorded as. That actually got up to speed pretty quickly, didn't it? Okay, so now if I click on export results, we'll see 2. Doesn't say that it was a constant thrust or a constant throttle here, does it? I don't know if that's really important though, because all the other stuff that it's recorded is what's important. Alright, so okay, so we've got 4 results on here now, and if I come in here and do upload has been received, thank you, and then if I click refresh, we should see now we have 2 more results, and they are using my new prop that I added. So this is 50-45 2-blade plastic, number of samples, throttle in each case, and thrust and all that kind of stuff. So this could fairly easily be made into a graph, but you need something to compare against, and this is where what I was saying before about Ryan's site, it's really good because you get a set of a whole bunch of different motors that have been tested against each other on the same equipment with the same standards and everything. So this might be just sort of interesting to look at just in passing maybe, but I think what Ryan has going is a lot better as a source of a genuine comparison. But anyway, this is here if you want to check it out. I think that's about what I had to cover here, really, isn't it? What else have I missed? Have I missed anything? Oh, so that's those 2 pages there. You can find those from the GitHub main page. The sketch for the Arduino is on in here. So it's just a few files there. Oh, yeah, one thing I will mention. This whole business with the analog to digital converter, it does look a bit complicated, and you might be more inclined to just use this normal analog in of your Arduino to read the voltage. So you'd use a voltage divider and you'd just use analog read. I think I mentioned something about this here. Here we go. So you can also use analog pins of the Arduino directly to measure voltage, and it works, but the resolution is not very good. So I went into a fair bit of detail there, but so if you don't want to use one of these analog to digital converters, you don't really need to, but it gives you a lot nicer results, and they're not, I don't think they cost that much. What was it? $4, yeah. So they're not really super expensive or anything, but if you can't be bothered, you don't need to be bothered. And I've put links to some general info about this kind of thing for each of the components that was that I thought was worth looking at. I found some good pages that you can probably get a lot more info than what I've got on my documentation there. But this it's all details there. It's quite nice. Yeah, so I think that's about it. Yeah. So I don't really have any plans to do a whole lot more work on this in the future. I certainly won't be doing anything on this. There are a few things that I've thought of for the app itself, for this app, that would be nice to have. So I might do a little bit more work on this in the future, I think. Plus, I'm sure people will have suggestions about what else might be nice to have on it. So if you have any suggestions, put a comment on this video and I'll have a look. Anyway, thanks for watching.